Thank you for inviting me. I'd also like to thank Ingrid for pointing out a few things. The one thing that I wanted to relate to her presentation was that it wasn't green that that brought us to this work. It was two things. It was high quality science and just saving steps, not having to work as hard at some things. But nevertheless, it resulted in a green outcome. So supercritical fluid chromatography has been around for a long time. And people that do it marvel at the fantastic separations you can achieve using this tool. But at the same time, you know, it's always kind of been known for the detection part of it, detecting what comes out of the column, being a bit problematic, not as high quality as you would hope, and you know, not as easy as you would hope. So for us, you know, we're thinking about the science, getting that high quality separation, but at the same time, we've got to get a lot of work done. And if the detection doesn't work so well, we're not going to be able to get a lot of work done. So this presentation is about addressing those detector issues and getting the quality where we want it to be. So people have been trying, sometimes successfully and sometimes not, to interface chromatography to mass spectrometers. This worked pretty well in the gas chromatography days, and used devices like this, jet separator, so you're just essentially pushing everything through a small orifice, and then there's a small break in that path where a vacuum is applied to it. And believe it or not, the interfaces of mass spectrometers still, these are ones from the 50s and 60s, but the mass spectrometers still use similar approaches toward getting the sample in. It's gotten a little better. There's often multiple stages of this and various ways to help the transport. But things have evolved, but they're not as different as you might imagine. So let's first talk about SFC. Why do SFC? Why not do conventional GC or HPLC? Most people do reverse phase HPLC, by far the most common approach used, and certainly by us too. However, reverse phase is an excellent tool when you have a lot of grease on the molecule, or high logP, but once the molecule becomes fairly polar, you know, it becomes increasingly challenged to do. And you often see methods out there that are really fighting to just be able to barely be done with reverse phase HPLC. And ultimately, at some point, you have to turn to normal phase chromatography to do highly polar molecules that don't have much lipophilicity. So you want to get at those polar parts. You could do that in the traditional way with hexane kind of column solvents, but there appears to be a much better way to do it, and that is with supercritical fluid chromatography. So just think of supercritical fluid chromatography as the same as you would normally do with hexane, except you have substituted CO2 for the hexane. So whether it's with the traditional approach or by SFC, you can do very, very challenging separations and get very similar outcomes with either approach. But the real thing here is, can we detect what we want to detect, and can we get a lot of work done? Because, you know, we only get the check if we get a lot of work done. We're not going to keep that check coming if we're only getting a little work done. SFC is much, much faster than normal phase LC. You often have much greater analyte solubility, and really one of the very most important things that adds to the productivity of SFC is you can do generic gradients just like you would in reverse phase HPLC. So you can have a broad gradient and often get the answer the first shot. That helps quite a lot with productivity. You can't do that with hexane normal phase chromatography because the range of all the elution is in a very narrow band of solvent strength. So the gradient approach really doesn't work there, but it works nicely with SFC. There's another aspect that makes SFC much more productive than hexane approaches, and that's really the speed, but also the amount that you can load on the column. So CO2 is just a more versatile solvent than hexane. It will dissolve more things than hexane will. So what that allows you to do is put more on the column. So particularly if you're doing purification, more mass load means more work getting done, and there's quite a strong difference there. So despite these productivity gains, SFC is only as good as the detectors that can be used effectively with it. So we may get great separations, but if the detector holds us back, we're still not all that productive. The issues with the detection, UV has been noisy, raises the detection limit. LSD, people have struggled there too. Mass spec, while for SFC it works a little bit better than with hexane solvent in HPLC, it's nowhere close to what you get on a routine basis doing reverse phase LC-MS. The people that do SFC-MS usually use APCI, and it seems as though temperature has an effect here. So APCI is a very hot source. Ultimately, in the end, we need to get to do the work that we need to do. We need to get all three of these detectors working close, or maybe as well or better than they do with HPLC. So this is the story of how we got there. Here's the typical approach. You have to regulate the pressure when you do SFC, right? So to maintain supercritical conditions, you have to regulate that pressure. And then the way most you usually do the UV at full pressure with a high pressure cell, and then you split what comes out of that and make that up with a solvent and go to either ELSD or mass spec or both. That's the way it's been done for a long time. You can get detection to work in those cases, but it's just not anywhere near what you can get in a day-to-day basis with reverse phase LC. So one of the things that holds us back here is, analytical chemists, we're usually pretty conservative, and when we're talking about pressure, we try to avoid pressure, right? So people try to run the HPLC, with a nice low, safe pressure. But this really is not good for SFC. And the reason for that is the density changes quite a lot as a function of pressure. And you can see right in here where it's very common to operate SFCs, you can have huge density change with only a small change in pressure. Or another way to look at that is in terms of temperature. You can have just the variation in the room temperature can change that density a lot. It's hard to get reproducible results when the density is changing. And as a result of that, it's important to start out with operating at the proper pressure. And we would argue that this is out here where these density lines start flattening out, not here where they're almost vertical. And bottom line, we would say that's 150 bar at the column exit. So this has been studied. Terry Berger studied this a lot and studied the effect of the back pressure regulator too. But you can see noise is higher until you get up to some reasonable pressure. And this is the data that really leads us to believe that a minimum of 150 bar is the right pressure. So we started with the challenge, with the ordinary approach to interfacing these detectors. We were not really happy with it. No, I haven't really seen anybody that says that it works well. And we tried a lot of different things to try to understand why this was not working well. One of the things we wondered, is CO2 different? Is it not as inert as nitrogen? Is that somehow playing a role? Because some of the things we were seeing didn't make sense. We thought we should be able to control things pretty well with solvent choice that we're adding in as makeup. And it turned out not so. As a matter of fact, it seemed to defy what we already knew. What we knew with mass spec, the lower the viscosity of the solvent leads to the availability of more ions, just because you get a better aerosol as you're spraying it into the mass spec. But what we saw when we do this with SFC is that instead of lower viscosity working better, seems like higher viscosity works better. Wasn't making sense to us. It was just the opposite of what years of experience of doing LC-MS had taught us. So this led us to a different hypothesis, and that the real issue with detection is phase separation when the CO2 expands. So to put this hypothesis in pictorial form, and then also to show what we do about it, what we would say is the solution is not to go through the liquid phase of CO2 as you're going back to atmospheric pressure, but start at high enough temperature and pressure that you avoid that. So you go straight from supercritical CO2 to gas. And those are two very similar things. So they're very much like the same phase. And it's not going to result in droplet formations, droplets of CO2 being separated out. So if we're going to address this, since we have to address this hypothesis, we not only have to control pressure but temperature. We sought the help of some experts in heating, and we utilized these heaters to control temperature at various locations. So here's where we went with the connecting the detectors. Essentially the same with UV, but we also added the ability to control temperature before going in, and then heating, and then going through an expansion tube. This is a very narrow tube, but fairly long, nearly 1 meter long, but very small ID. And then expands on the way. It's only maybe 100 milliseconds of exposure time to the heat and the expansion, and then you just split into the detectors. And you can change that split ratio however you want, depending on whether your focus is sensitivity on one or the other. So we've got our hypothesis, we've got our apparatus built to test the hypothesis. Now we need to test it. We thought the fixed restrictor would be more complicated than it was, but it turned out to be quite simple. We thought we'd need multiple restrictors, but it turned out we didn't. And the reason for that is once we've heated things up before entering the restrictor, we're 100% supercritical, so things really don't change. You change, it doesn't really matter what the solvent composition is so much. You get the same back pressure and outcome with one apparatus. So we characterize this. This is just pressure as a function of flow. Not surprising. I mean, ultimately we have to regulate pressure and flow to do the chromatography, so we need to find out the sweet spot, which is right in here at about 4 mils a minute. Also we noted we're not following Darcy's law here, which is no surprise. So we went further there. Now we're looking at the restrictor itself up top, and then we're changing our mobile phase composition, changing the amount of alcohol in the mixture. So you can see for the detection part, the restrictor, we're under supercritical conditions, but in the column where we're at lower temperature, we're not. So we thought the heating would be pretty simple. So when we started heating, we were just heating things up, and the more we heated, it just looked better. We thought, well, this is going to be easy, right? Just keep turning up the heat. It turned out to be a little more difficult than we thought. We had to go through and do some iterative optimization, and we found that we weren't going high enough in temperature to get fully optimal results. One of the things that we wanted to do was to really prove our hypothesis to the extent we could, or at least redemonstrate it. And here's a way we did that. We did a 4-compound mixture, and we normalized their concentration so they all gave the same response in the ELSI experiment. And then we went back and did the SFC as a function of temperature after the column. And we could see the same effect. So what we could see is that indeed higher modifier, which is higher velocity, actually gave higher response. Exactly the opposite of what we see with HPLC MS, but it confirmed our observations there. And that what we also saw is that once we got up to a sufficient temperature, we renormalized all those concentrations. So it was a nice reconfirmation of our viscosity effect being exactly the opposite of what we had seen and known for a long time with HPLC. So then, it's just a matter of optimizing sensitivity here. You can see we really have quite a lot of improvement in the mass spec as we heat things up and as we push that transition arrow from going through the CO2 liquid phase out to where it goes from supercritical to gas. We tested a lot of different configurations, heaters just about everywhere. What we found in all cases, one heater right before the expansion is the optimal setup. Multiple heaters not helping at all. So we also looked at the classic things you might look at with mass spectrometry. So gas flow within the source. And we can see for HPLC, we get the normal expected kind of curve. With SFC, we find that optimum is with less gas flow, and then we see some tailing off at higher gas flow. We would interpret this to mean that the CO2 gas we've already got in the eluent is helping. We don't need as much extra nitrogen there to create the proper aerosol. Right, and we then of course did the same thing with EOSD. Now in this case, we're using the EOSD at what we knew, which was reverse phase LC conditions. But we could still got some useful data here. We could see for very small molecules, there was a limit at which the signal went away in terms of the temperature. But still promising nonetheless. But like many of this, the parts of this, we found that we needed to re-optimize, and where we needed to go is now back to the OSD detector, because what were the right conditions at the detector were not the same for SFC and LC, and what we can see is we have once we cool the OSD down some and lower the gas flow some relative to reverse phase conditions, we can see that we're not dropping out that small molecule. And now we can measure an optimum also, and interesting enough, that optimum appears to be right where it is for the mass spec detector too. And it should be no surprise, our goal is here is to form a really good aerosol. So both detectors want a good aerosol, and both seem to get it under the same conditions. All right, so what about UV? UV is different. We can't control the temperature nearly as much there. What we do know about UV is it's generally shot noise limited. So we may want to take a different approach altogether here. And that led us to look at temperature, but in this case we looked at temperature in the opposite direction, lowering temperature. So noise has always been a problem in UV with SFC, and what we found is by cooling the eluent before it goes into the UV detector, we can actually lower that noise quite a bit. Okay, so now just some examples. And here with the UV detection, here's a comparison. Here's what we're doing with SFC. Nice signal to noise, nice signal to noise there. We can do the comparison with HPLC. We're not quite to where we can get with HPLC, but we're pretty darn close. Within a factor of 5 there, and this is without the cooling. You can get that down to about a factor of 3 with the cooling. And we did the same with EOSD. We're getting really nice noise comparison there, and you can see with EOSD, actually the SFC comes out better than the reverse phase liquid chromatography. And then, of course, with mass spec, first we compared the past with the new interface. In the past, sure, we could do mass spec, we could get signal. Wasn't a lot of it, not as near what we would hope for. Now this is a fairly challenging assay. We're doing plasma bioanalysis, but it's not the separation that's the challenge. It's really just having the sample enter the ion source of the mass spec under the proper conditions. So once we tried our approach out, the signal went through the roof. So taking that example a bit further, we did lots of bioanalysis. This is from a pretty big study, and we thought we have all these samples, let's just run them through both instruments and get a nice comparison. The bottom line is we essentially got identical results, whether it was LC-MS-MS or SFC-MS-MS. We could see small differences here, and we're able to readily attribute those to the solvent. So to do the LC-MS, we had to use methanol, and to do the SFC-MS, we had to use IPA, and that accounts for that last factor of 2 in sensitivity. But the heated interface brought us orders of magnitude there, so it got us really right to where we would expect to be. We essentially normalized the response between the two separation approaches. So in summary, I guess I would say the detection works almost as well UV, better EOSD, and pretty much exactly the same. And we've proven that down to 100 picogram per ml. We haven't gone lower than that, but that encompasses nearly all the work we do. So again, here's the setup we use. I've taken the other devices out, so it's really simple: heater, expansion tube, and then into the detectors. So just a little bit about outcomes. So this gave us enough comfort that we thought we could deploy this not just in our own lab, but out to other relatively untrained chemists, and that has been very good success. So here's some example data. You can see there's a good reason to want to use SFC, because sometimes LC, reverse phase LC, just can't get you the separation you want, whereas you can get a huge one with SFC. Here's another example, and here's where the data often looks the same. So very frequently you can take SFC and LC and compare the data, and this is often what you see. You have an impure mixture here using the technique you're comfortable with, and you get essentially the same chromatogram with SFC, except the peaks are reversed. Right? So it's same chromatogram, but like you printed it out on one of those old transparencies and flipped it over. And again, you actually see the difference in the LSD here. So these are eluting at fairly high water concentration. So the ELSD doesn't look so good, whereas SFC, perfect. So here we wanted to test this applicability. So we took a 1,536 library of compounds, did LC-MS, SFC-MS on all of them, and 96% gave exactly equivalent results. The only difference is it looks like the chromatograms were flipped over. About 3% of those left, about 3% actually worked better by SFC, and that's really, I would attribute to the compounds we were looking at. There's a little bit more bias toward polar compounds than greasy compounds. So the conclusion here is there's huge overlap between the two. So not only can SFC do this unique work, but it can cover a lot of your work. Yep. So software enables that. So things are easy. Here's a chiral example, 12 different runs, 3 columns, 3 solvents, or 4 columns, 3 solvents. Can quickly find a chiral separation there. And then just to conclude, I'd like to say SFC is highly capable of doing excellent separations, highly complex chiral separations, but at the same time it's very broadly applicable, like reverse phase HPLC. It is the next go there first analytical technique. The other thing I'd like to point out, it's green. So for SFC, 75% of the solvent use is CO2. We take it out of the air, and then it just is returned to the air. Quarter the volume of waste is 1/4 the waste disposal cost. And for us, we do all of our SFC with alcohols, just the first 3 carbon alcohols. So we probably are using, what solvent we have left is probably about the friendliest solvent we can use. Thank you.